Hi, I'm Olivia, everyone's favorite math teacher, and in this video we're going to talk about horizontal asymptotes and the end behavior of functions. So here's everything you kind of need to know about how we view horizontal asymptotes from a calculus standpoint. Now, in algebra, you would typically look at a horizontal asymptote and you would say, well, as my x approaches infinity, my graph kind of approaches a value, and you would estimate it based on what it looks like. And we kind of do something similar in calculus, except because of limits, we can actually calculate precisely what that value is. And the reason that's valuable is because just like we didn't like looking at a tangent and going, well, from this table, we can kind of say that the value is approaching a point and, well, okay, that's close enough. Everybody was, not comfortable with that idea of the imprecision. And these horizontal asymptotes are the same thing. We don't like the imprecision of going, well, it's kind of doing this. Because what happens if something weird happens over here as we get super close in and the graph kind of explodes? We saw an example of that with our limits, where it looked like we were getting close to something, but when we zoomed in really close, we saw that no, something weird happened and it just kind of went weird at a point, right? We want to be able to calculate these. And thankfully, we have a theorem that allows us to do that if we can cause our functions to turn into rational functions. So one of our goals here is going to be, if we can take a function and then convert it into a system that will look like either a rational function or something we can take the limit of, then we'll be able to apply all of our normal limit rules in order to figure out what we're approaching as we go towards infinity. So we're going to be using kind of either change of variable situations here or other kind of situations that will let us convert into this situation here, where we will know that we can reduce down to a zero situation. And then, applying our normal limit rules, we'll be able to evaluate what goes on as our function approaches infinity. Now, this part down here in the bottom, I kind of combined both of our precise definitions of the function as we approach infinity here. So this is basically the epsilon delta for our horizontal asymptotes, okay? So basically what we're saying here is that we're going to let f be a function that's defined on some interval, and then we either are taking the limit as x approaches negative infinity or the limit as x approaches positive infinity, okay? And then if we're talking about the negative infinity, so going to the left, then for every epsilon greater than 0, we're going to say there exists a delta such that when x is less than delta, so we basically pick a point, and we say that as long as x is over here, then we have said that there's an epsilon where we will be within that epsilon. That x value will be in there. We can say there's some value that we can go out here and yes, we'll be in there. And that's just what this limit says, is that, yeah, you tell me how close you want me to get to that asymptote, and I can find some value out there somewhere that will get me that close, okay? That's what the limit is saying, is that I can, in fact, calculate and find that point if you just tell me how close you want to get. And this is a little bit different from the kind of fuzzy value of going, yeah, I can get close enough. This is going, no. I can find the exact number, okay? And that's what the epsilon delta proofs let us do. Now, what we're going to do is we're going to go ahead and apply this theorem as well as our previous just general algebraic ideas with our limit laws that we learned before to go ahead and see how we calculate some of these. So here's our first example of that theorem in action. Now, on the top, I've tried to do it without using the theorem. I've tried to do it with no tricks, just simply applying our limit rules. And you see that we run into that problem I talked about where we attempt to use infinity like it's any other value. And we can't, right? So when we just try to apply our limit rules, we apply the limit, we throw the limit in here, limit of the top over limit of the bottom, we throw the limits in, and when we get to this limit of x, we get 3 times infinity 2 times infinity, that'd be infinity over infinity. And at this moment, we really don't have a way of dealing with that, because that's an infinite over an infinite. Is like, what is that, right? Well, I don't know. So instead, we get a little tricky, okay? We throw some algebra at it, because if we can make it fit one of our theorems, if we can make it fit one of the forms where we can do something with it, well, then we can kind of get around this whole infinity situation. And so in order to do that, what we want to do is we want to simply take all of our x's and we want to move them into the denominator. Because if we can do that, we're good to go. And in order to do that, all we really need to do is multiply everything through by our fraction, where the greatest power of x is in the denominator. And we're always allowed to do that as long as we're using a fancy version of 1. So in this case, I simply use 1 over x divided by 1 over x. Because, hey, that's just 1 as long as x isn't 0. And in this situation, x isn't 0. It's approaching infinity, but this is a limit. I'm approaching infinity. I'm not equal to infinity. So again, the limit to the rescue. I can do something in calculus that I can't do in algebra. Okay? So run it through, divide it out, and in the front I get 3 over 2, but in the back I get 2 over x and then 1 over x. Now I can apply that theorem that we just learned. So when I bring my limit through, well, the limit as x approaches infinity, there's no x here, so when I throw my limit law into here, that's just going to be 3, and that's just going to be 2. And when I use that new theorem, well, here, 2 times the limit as x approaches infinity of this, that's 0. 2 times 0 is 0, goes away. This is 0, it goes away, and I'm left with 3 over 2. Now, I would suggest you check out that function in Desmos or on your graphing calculator and do the same algebraic examination that you would have learned to do in Algebra 2. And you'll see that, sure enough, your function, as you go towards infinity, approaches 3 over 2. And if you remember the rules you learned for finding horizontal asymptotes, that because the degree of my numerator matches the degree of my denominator, I would divide my leading coefficients, and yeah, 3 over 2. So if you ever wondered where that rule you learned in Algebra 2 came from, or if you asked your teacher and they either didn't know or they told you wait till calculus, now you know where it came from. So let's look at another example where we do something also tricky, but a little bit different. So for this second example, see if you can figure out what you need to do to solve this one. Because obviously, you can't just throw your limits at it. You need to do a little bit of algebra first. And I'll show you what we do in 3, 2, 1. So when we look at this one, we don't really have a way of converting all of these over into the reciprocals the way we would want. Because remember, we had to multiply by 1 over x divided by 1 over x. And we can't really do that here. It's not going to do anything for us, because that would give us 0 in our numerator. And, well, okay, then we get 0 divided by 0, and that doesn't help us, right? That's, again, an indeterminate form, and we can't do anything with that. So we need to see if there's a way for us to change things up. So the first thing we do is we try to figure out, okay, can we modify things around? And the easiest way to do that is notice that, well, we've got a subtraction here and we've got a square root here. So we try to use our conjugate. And in doing our conjugate here, we mess things around and we get an x in the top. Well, that did reduce our numerator, and we did keep this in the denominator that we can use our trick with. Well, that actually gives us an advantage, because that lets us have a numerator that will not be 0 when we utilize our trick, because that will go to 1. So now we're not going to get 0 divided by 0. So as long as the numerator doesn't also go completely to 0, we're good to go. And we know that won't happen because we have this 3x here. So we know that won't be 0. So at this point, we know that we're good not to get an indeterminate form. And if we had looked at this graphically, we also know that we're not going to get an indeterminate form because we know that this goes to a value, right? But again, we're trying to do this without having to look at the graph first. So use our conjugate, divide through by our 1 over x, and when we do this, this is the other tricky part because this is a square root. So when we divide through by the 1 over x, it comes into the square root as a 1 over x squared. So when that divides through, we get 9 here and then 1 over x here. So then when we bring our limit in, this part goes away and we get the square root of 9 plus 3, which is just 6. And we get that the limit of this as x approaches 0 is 1 over 6. A nice calculable value. So I'm going to give you 2 to go ahead and try, and I will give you a hint on the harder one. And you'll see the answers to those after the outro. Give these 2 a try. And on the bottom one, it is a little bit tricky, but it does look like something that we have proven in a previous video, if you can figure out the change of variables. So I hope that overview of horizontal asymptotes and how we can calculate them with a precision was helpful. If you are having difficulties or you have any questions, remember you can drop down into the comments or join us on Discord. And as always, the answers to the last problems will be after the outro.